Good evening. Welcome to the QCIS channel. Where on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and tonight we're going to get into some more astronomy. Now, earlier this week, we actually, here in Indiana, saw a total eclipse of the sun, something that doesn't happen very often. But something that is really rare, particularly here in the lower 48 states, are what we call northern lights and southern lights. Now, let me get into some information, share my screen, and they're known as auroras. Now, just want to ask you this question. Have you ever seen the dazzling, dancing lights of the aurora in the night sky? Well, the reason why you can't see them here because you're not close enough. Now, in order to see them, you have to be closer to north and south poles because you have the greater chances of seeing these amazing spectacles. Now, the northern and southern lights have two different names because of the hemispheres. Now, in the northern hemisphere, the northern lights, they're known as aurora borealis or northern lights. Now, in the southern hemisphere, the southern lights are known as aurora australis, or we know them as the southern lights. And there's a picture of them from the sky. You can see the telescope or you can see the satellite. But basically, here's one thing you must understand. There are causes to auroras. Now, what causes auroras? Now, just like we talked about the eclipse, well, you have the magnetic field. This is what causes all the auroras here. You have your aurora oval and your magnetic shield. And you have your solar wind, your solar eruption. And what do I mean by solar? Mean lights, sun. So basically, auroras are a natural interaction between the sun and Earth's atmosphere. Now, our sun generates a strong solar wind, which carries about 1 million tons of extremely hot plasma. Now, in that plasma, you can find electrons, protons, and other particles. Now, away from the sun every second. Now, in the Earth's magnetosphere acts as a shield that protects us from the constant wind deflecting it from the Earth. So, during a solar storm, such as a flare or coronal mass ejection, a large amount of plasma hurls through space at high speeds as part of the solar wind. When this extra solar energy collides with the Earth's magnetosphere, some of the electricity or electrically charged particles, again, some of the electrically charged particles move down strong magnetic field lines at the north and south poles and become trapped in the Earth's atmosphere. Now, what happens after that is these particles bounce from the North Pole to the Sun Pole and back again, transferring energy in molecules in Earth's atmosphere as they go. Now, the colorful glowing lights, again, the colorful glowing lights, the colorful glowing lights of the aurora result when these energized molecules release their extra energy. Now, Why are auroras different colors? Well, auroras within one of the Earth's atmospheres, or let's go back, auroras basically occur within one of Earth's upper atmospheres, and the atmospheres are in layers. So again, auroras occur within one of the Earth's upper atmosphere layers, and it's known as the thermosphere. Now, solar particles trap here intact with different types of gas molecules. Now, that gas is mostly nitrogen and oxygen, and that results in unique color displays at night. Now, what happens is the oxygen gives off green and red light, while the nitrogen glows blue and reddish purple. Green colored auroras are most frequent, resulting from interactions with oxygen molecules at lower altitudes between 100 and 300 kilometers, or 62 to 180 miles, while less commonly occurring red auroras form interactions with higher altitude, which is above 300 kilometers or 180 miles for oxygen molecules. Now, do auroras affect Earth? Well, auroras have delighted and inspired curiosity in humans throughout time. Now, the only significant impact of Earth associated with auroras is a possible disruption of radio communications, as charged particles from the sun create a disturbance in Earth's magnetic field. Now, when the magnetic disturbance is particularly strong, auroras can sometimes be seen from the poles in mid-latitude locations. Now, when we talk about mid-latitude locations, we're getting a little further from the poles. Now, something you need to know. Earth isn't the only planet that experiences auroras. Any planet with an atmosphere and a magnetic field is likely to have auroras. Spectacular auroras have been observed on Saturn and Jupiter. And you know, Saturn is nothing but gas. So that's basically what you have when we deal with auroras. Now, what I'm going to do, I'm going to go back, show you some videos out here of northern and southern lights explained. Now, again, we're going to go ahead and share my screen here. Just bear with me. Right. Now, these videos are for educational purposes only. Fair use, fair use.
Perhaps you've seen these videos online. Some especially stunning aurora have been dazzling YouTube viewers these past 2 weeks. It's as if space is painting us a beautiful picture. Or just showing off. We talked to our resident space expert, Dr. Ian O'Neill, to find out how these are created, where you can find them, and why now.
Basically, the sun's surface is currently going through quite a lot of magnetic activity because we're approaching solar maximum, which is part of the 11-year cycle. Very natural cycle, there's nothing scary about it, and we're approaching the maximum activity, and that's going to happen in about 2013.
The sun's kicked into high gear, causing enormous eruptions of solar wind and plasma that are aimed right at us.
It impacted our magnetosphere. That's the magnetic shield that surrounds our entire planet. Now, if the conditions are right, and when this magnetic bubble, this coronal mass ejection, hits our magnetosphere in a certain way, it can inject solar plasma into our magnetosphere, and that funnels into the polar regions. And when these plasma, these are basically mainly protons, high energy protons, when they hit our atmosphere, they generate light. And when each one hits, you get this fantastic aurora.
These aurora are being seen in northern latitudes, like in Sweden, and near southern latitudes, like in New Zealand. But can they ever be seen away from the poles, say like the Midwest?
It is possible. It depends on the ferocity of the solar storm. And it has happened in the past, apparently back in the mid-1800s. The Carrington flare event, it was the most historic solar flare in that it was huge. I mean, it was record-breaking. It was actually observed during daytime, and the coronal mass ejection only took a few hours to hit Earth. Apparently that produced aurora at very, very low latitudes, and at night in like the Midwest, people could read their newspapers at night because it was just that bright. So it is possible, it's just extremely rare.
NOAA can actually predict space weather daily. Hop online here to see how likely a big aurora is near you. For Discovery News, I'm Martin Berman, and that's Aurora Borealis and Australis Explained.
Again, we're dealing with space, and of course the sun is involved. And what I'm going to do is show you a video on what makes northern and southern lights different. Now, most of us have heard the term northern lights. We haven't really looked at southern lights. But in this next video, I'm going to find out what makes northern lights and southern lights different. Fair use, fair use.
Okay, so what we investigated in this paper is that we looked at images of the aurora from the northern and the southern hemisphere at the same time. So if we see the northern hemisphere from above, like this is Earth seen from above, and here is the southern hemisphere seen from below. And then we found that we had this, if we had a symmetric aurora, when this event started, then you would get an aurora happening here and happening here at the same time. So at exact same location, but we had chosen events so that the onsets of these events were asymmetric, so that it looked like that. This in the beginning, you had aurora located here, more towards the dawn of the, and more towards dusk here in the northern hemisphere. And they are sort of displaced from each other. And then we looked at how this evolved through these events. And what we found was that these actually became more symmetric as these evolved. So at some later point, it maybe looked like this, with these becoming north-south symmetric. And this has been observed once before in one event study, but what we had done here is that, for one thing, we had identified multiple events where we could see the same thing happening over and over. And also we managed to relate this to activity in the magnetotail. So we could actually see that if we had a lot of activity, then this return to a more symmetric state happened faster. And if we didn't have a lot of sort of closing or flux, or what we call it, in the tail, then these didn't become symmetric at all. Then they actually just stayed as they were initially.
Now, basically what he's talking about is, you have the Earth. He drew actually two circles, but the Earth is very spherical. And when we deal with symmetric, we deal with, if you cut something in half, you're going to get a mirror image of the other. So if you have northern and southern lights happening at the same time, they're going to be the same width, the same length, and you're going to be able to see them at each of the poles at the same time. Again, basically, when it comes to northern and southern lights, if you're going to see them, of course, you're going to have to go down there to relatively cold climates. I got to tell you that. Fair use. Let's continue.
So that's the new part. But the reason that this is exciting is that earlier we have thought that the asymmetry in the system enters the magnetosphere by a mechanism called reconnection. And what this paper shows is that it's possible that it is actually the opposite, that this reconnection in the tail is actually reducing these asymmetries. And that would change the way we think about how the asymmetries enter the system and how they are removed from the system. Because the same mechanism can't make the system asymmetric and at the same time make it more symmetric. So this is telling us not only how the system sort of relaxes to its initial state, it can also say something about how it becomes asymmetric in the first place. So currently I'm in my final year as a PhD student. So I've currently done one research article, and I'm working on my second and my third sort of simultaneously, trying to get them finished before my deadline. I mean, in some ways it's really exciting, and it's also a bit scary if it's sort of if it can be controversial and all these things. If I get the opportunity, I will certainly continue doing this kind of research. I find it really interesting. So.
Again, what you just saw was an explanation. Of course, there was a PhD student. He's going to do his dissertation on what's going to happen with the northern and southern lights. But basically, to sum it all up with some common sense, you have oxygen, you have nitrogen, you have magnetic fields around the earth to keep the sun storms or the solar storms from reaching the earth. And if there's atmosphere, basically you're going to see lights. Now, they're fantastic lights. I mean, most of us, let alone the solar or lunar eclipses, we will never see the northern and southern lights because we're not close enough. But if there is a storm, it could be a chance that we could see them here to Midwest. But you have to remember, when it comes to these northern and southern lights, it depends on the hemisphere. Now, what do I mean by hemisphere when it comes to the Earth? Well, as you know, you have your poles, and then your largest area or your largest circumference is the equator, which is your 0-degree latitude line. And I believe your prime meridian is your 0 degrees longitudinal line. But basically, and this might go a little off of the subject, but if you think about it, because of the hemispheres and the way the Earth tilts, this is why our seasons are crazy. Because right now, it's spring in the northern hemisphere, where it's fall in the southern hemisphere. And when it's summer here, it's winter in the southern hemisphere. When it's winter in the northern hemisphere, it is summer in the southern hemisphere. If it's fall in the northern hemisphere, it's going to be spring in the southern hemisphere. And the Earth has a lot to do with your eclipse, whether it is a lunar or solar eclipse, and your northern lights. And it is the atmosphere. This is why we try to protect our atmosphere. So basically, as I go ahead and share my screen again, when we deal with northern lights, or even southern lights, or auroras, this is the map, this is what you have. Auroras, again, are a natural interaction between the sun's and Earth's atmosphere. And of course, if you understand our sun, well, our sun generates a strong solar wind, which carries about, I just mentioned it before, 1 million tons of extremely hot plasma. Now, within that plasma, you're going to have your electrons, protons, and other particles. and that's away from the sun. And you have the magnetosphere. That's actually what protects us from constant solar winds because the winds are deflected from the earth. Now, again, when we have those lights again during a storm or a solar flare or any type of coronal mass action or mass ejection, this is when you get a large amount of plasma that's hurling space at high speeds. And this is what also, generates some electrically charged particles. And of course, they're going to move down the magnetic field lines and they're going to be trapped in the Earth's atmosphere. And this is where you get the northern and southern lights. And that concludes this video on northern and southern lights. Very short tonight since it was astronomy this week because of the eclipse. I wanted to get into some more astronomy. So I dealt with the northern and southern lights. Now, if you like what you have been presented tonight, please comment, share, and subscribe. And if you are looking for content that's a little more on the political side, relationship side, or social side, check out my main channel, the 411 Talk Zone Radio Show channel. Now, once I record all of my videos from the 411 Talk Zone Radio Show channel, and of course, the QCIS channel, I will upload those videos to my X page or Twitter page. I almost forgot. Twitter, which is now X. Now, because this channel, the QCIS channel, is an educational channel, I'll also post videos that I record on this channel to my LinkedIn page. Now, again, I know there are some individuals on my LinkedIn page, they want to have conversation. If it's going to be about STEM or getting into the fields of STEM, I will listen. But if it's just social talk, that page is not for social talk. It's for actually networking for jobs in STEM. If you want to learn more about STEM, you can go ahead and shoot me a connect and I'll answer it. But that's the only way. But for the most part, just take a look at the information that I post. And you look at the videos, put a comment. You have any other questions, just leave in the comment section. I will answer. But make sure your comments are pithy. Make sure you look at the information before you ask a question. I don't have a problem doing the work for you, but make sure you make the effort. There's some people that want me to do all the work for them. Again, the QCIS channel, this is an educational channel. And going back to the videos, I call it my astronomy week. Tonight, I just featured a couple videos on northern and southern lights. And many of us have never seen them, but they do exist. And again, I want to thank you for viewing this content right here on the QCIS channel. On this channel, I give you a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. You all have a wonderful and gracious evening. And God bless you. You have a good night.